When the holidays start to feel a bit repetitive, reach for a Sprite Winter Spiced Cranberry and put your twist on tradition. A bold cranberry and winter spice flavor fusion, Sprite Winter Spiced Cranberry is a refreshing way to shake things up this sipping season. And only for a limited time. Sprite. Obey your thirst.
Every Who down in Who Newville liked the holidays a ton. But where to get great prices on gifts, they had no idea. None. They searched and they searched for great gifts under $25. Gifts for spouses and friends and even their toddlers. When suddenly one Who shouted, Walmart has what you want, knowing they have Lego, Tree Hut, and low prices to flaunt. So they enjoy the holiday season as Who's often do. Cheering and shouting, Walmart has incredible gifts. Who knew? Find gifts they'll love under $25 at Walmart.
People love images, right? And so images of Jupiter, images of Saturn, images of the rings, they're really visually appealing. And people love Mars because there's a chance we could go there. There might be a past history of life, And people love Venus because it's really mysterious. It's shrouded in clouds. We can't see the surface. It's got this toxic atmosphere. And then there's Mercury.
Suzie Imber is a professor of space physics at the University of Leicester and is a key scientist involved in the third mission to investigate Mercury, called BepiColombo. Suzie is on a bit of a mission herself to emphasise the importance of studying Mercury, even though it's not always a fan favourite of the planets in our solar system.
If we're looking at planets orbiting other stars, which we are, we're searching for these exoplanets. Could they harbour life? What do they look like? Then Mercury is the closest analogy we have in our own solar system to some of these exoplanets. We're really good at finding exoplanets close to their star. That's how our instrumentation is biased. And so we can use our knowledge of Mercury to help us understand these other planets orbiting other stars, which means that the extent of the science we can learn from Mercury goes all the way through to astronomy and astrobiology and covers lots of different features.
We're bringing you this month's From the Theatre episode from the Space Park in Leicester, where we spent the day producing some very exciting content in anticipation of this year's Christmas lectures all about space science. Suzie, thank you for joining me on this special episode from Leicester. Space weather is your specific area of physics that people might not be that familiar with, and it involves observing the effects of the sun on other planets, which is predominantly in the form of solar winds. But before we get into talking about that in the context of Mercury and the aims of the BepiColombo mission, let's get the basics down first. How do we experience solar winds on Earth?
The solar wind is coming out of the sun all the time. It takes 2 to 3 days to reach the Earth. It travels at about, on average, 450 kilometers every second. And it carries with it the sun's magnetic field. There are also particles there, but not very many, about 5 to 10 in a volume the size of a sugar cube. So it's very rarefied particles, protons and electrons predominantly, and this magnetic field. And that's what the solar wind is. And it's always coming away from the sun. And so the Earth sits within the solar wind. In fact, the solar wind extends all the way out to the edge of the heliosphere, well beyond Pluto's orbit. So we sit within this magnetic field and particle environment. And around the Earth, we have our own magnetic field. And space weather is really the interaction between the solar wind and our own magnetic field.
So you mentioned heliosphere there. When I was looking into research for this podcast and what BepiColombo was doing, I found it difficult to differentiate between a lot of the sphere words that get thrown around when you're talking about space. So you've got atmosphere, heliosphere, magnetosphere. Mm-hmm. Could we try and differentiate between those to start with, and what is the largest sphere scale and then where the other ones fall?
Yeah, of course. So the heliosphere is essentially defined as the furthest point dominated by the solar wind, actually. And so within the heliosphere, we have space that's dominated or filled by the sun's magnetic field and its particles. And beyond the heliosphere, we are in the interstellar medium. So this is huge. This is a huge volume well beyond all of the planets in our solar system. And indeed, this was theoretical, but recently we saw one of the Voyager spacecraft cross the heliopause. So leave our own solar system, leave our own heliosphere and enter the interstellar medium, which we had to wait decades to observe because it took so long for our spacecraft to get to the edge of the heliosphere. So that's the sort of biggest of the spheres, as you put it. And then magnetized planets have their own magnetospheres. And so a magnetosphere is just the volume of space that's dominated by the magnetic field of that body.
Sure.
So the Earth's magnetic field is a huge bubble around the Earth. It's not spherical, actually. It's more sort of bullet-shaped. But it's not set in stone. It moves. So the extent of the Earth's magnetic field or magnetosphere is governed by the balance between how hard the solar wind is pushing and the Earth's magnetic field. And so if the solar wind pushes really hard, the magnetosphere shrinks towards the Earth. And if the solar wind doesn't push very hard, the magnetosphere expands. So it's not set in space as a boundary that's always in the same place. It moves around. And then as we head towards the Earth, of course, we get the ionosphere and then the atmosphere, which we're pretty familiar with.
The planet with the most similar magnetic field to Earth is weirdly Mercury, which has come as a bit of a surprise to scientists. Why is it that we have this similarity in our magnetic fields?
You might expect to have a really close similarity between the Earth and Venus, for example, because Venus, we think of it as the Earth's twin. It's not very far from the Earth. It's about the same size. It theoretically should, perhaps you might expect to have the same characteristics, but it really doesn't. And one of the things you need for a magnetic field is, or a dynamo, which is what generates our magnetic field, is that the body needs to be rotating. And Venus has a rotation rate of, I think, 243 days, perhaps, but it also spins in the opposite direction to the Earth, which is kind of interesting, but it's spinning really slowly. The Earth is spinning once every 24 hours, and so that helps with our dynamo. There are lots of other features as well, of course, that you need to generate a field, but that's a really significant one that the Venus doesn't have. We also need to have the ability of a planet to cool. So we need to have convection inside the planet. Venus is very hot. It's got this very thick atmosphere. It doesn't have plate tectonics. And so those things act in the Earth's favor and help us to have our own magnetosphere where Venus doesn't. Mercury is a slow spinner, so it does rotate. It rotates slowly, but just about enough to be able to generate a very weak magnetic field. So the other one to mention, of course, is Mars. Mars, we think, used to have a magnetic field that looked very similar to the Earth's. But about 4 billion years ago, it lost its magnetic field. And that led to this trajectory of Mars's environment from something that was probably quite similar to the Earth's to the way that we see Mars today. So the magnetic field is actually really important in keeping an atmosphere, for example, and habitability of a planet. Mercury is not habitable. It's very hot. Its day side is about 450 degrees Celsius. Its night side is minus 150. So it's not a habitable place, but it does have this very weak magnetic field. And as you correctly said, its magnetic field is similar to the Earth's in its structure.
On to BepiColombo and having a harder look at Mercury. This is only the third mission ever dedicated to investigating Mercury. When you compare it to other planets like Mars, which has, I think, between 40 and 50 missions that have investigated Mars, what makes it challenging to study Mercury? Why has it been studied maybe less than the other planets in our solar system?
That's a really good question, and I would argue it should be studied more, of course, because this is my area of expertise. Yeah. But there's lots of reasons actually why it's been really difficult. So if you think about the way that you explore a new planet, traditionally what we might do is send a mission to fly past that planet to take some observations as it goes past. And we did that with Mariner 10. It had 3 flybys of Mercury in the 70s and gave us sort of our first tantalizing glimpse of Mercury's environment. And then we sent back a mission called Messenger, and that arrived in 2011 and was there for 4 Earth years. And that had a much more advanced instrument suite. So we used the flybys to tell us what kind of instruments we wanted to send back on an orbiter. And then we sent those instruments back. And BepiColombo is the next in that succession of missions, and it's far better instrumented. And it uses the lessons that we learned from the previous missions to help us design how best we can explore Mercury's environment, because what we realized pretty quickly with Messenger is that we really need 2 spacecraft to understand Mercury's environment. We had a lot of compromises with the Messenger mission. We had some people who wanted to be really close to the planet and using cameras to look at the surface and surface geology and features. And then we have people like me who want to be quite far away and understand the magnetosphere and space weather at Mercury. And a single orbit is very difficult to keep those two people happy. Mm-hmm. And so the orbit that was selected was the best possible compromise between these two and many other scientific objectives, also enabling your spacecraft to not overheat. Because if you are in an orbit that's very, very close to the planet continually, then you have a risk of your instruments overheating. And so sort of a combination of the thermal concerns and the observational constraints led us to the eventual orbit that was picked. But with BepiColombo, we're sending 2 spacecraft back. So one of them is a European spacecraft, and it is going to be quite close to the planet and will be exploring the surface features, for example, in incredible detail. And then there's a Japanese spacecraft, which is a smaller spinning spacecraft that will be further away. So not only will we allow people to analyze Mercury in the correct location for the science they want to do, but we can also have conjunctions between the 2 spacecraft that enhance the possible science. So from my perspective, for example, I might have the smaller spacecraft looking at what's coming from the sun, and that's the Japanese spacecraft. And the European spacecraft would be monitoring the impact of that space weather on the planet itself. So I can see what's coming and I can see what then happened. With a single spacecraft, you either see what's coming or you see what's happened, but you never know both. And so that makes cause and effect really difficult. So that's one of the reasons why we're sending this particular type of mission back to Mercury. I think one of the reasons that we haven't really explored Mercury that much is that it's really hard to get to. Mm-hmm. So we're heading in towards the sun. So we're falling into a gravity well, basically. And one of our big challenges is actually slowing down. We are going to fall and speed up and up and up as we approach the sun. And so instead of going straight to Mercury, and we could do that, we could be there in just a few months if we took a straight line. The problem is we can't stop. So we would fly past. Yeah. And that's not helpful.
And fly into the sun.
Yeah.
Right, which is ideal.
So that's not going to get us much data. And so what we're actually doing is, I think, 19 laps of the solar system. Mm-hmm. And as we go around, we go in sort of a spiral. So we're just gradually approaching the inner heliosphere, or getting closer and closer to Mercury. And we also use the gravity of the planets as we go. And as we fly past the Earth and then Venus, and then we fly past Mercury many times as we're approaching our orbit insertion, that means that we can use the gravity of the planets to slow us down and to change the direction that we're going in. So they help us to sort of bend our trajectory towards Mercury, and they help us to slow down. And so it's a really, really complex calculation to work out how you can get to this planet and be in a position at the end of your journey where you are close to the planet and going in the same direction as it at the same speed, so that you can be captured by Mercury's weak gravity and you can end up in a long-term orbit around the planet. And that has taken a long time to figure out. And indeed, our mission, which is called BepiColombo, is named after Giuseppe Colombo, who was the physicist that worked out how you get to Mercury. He's the one that plotted this trajectory and figured out how you can do all these flybys and this complex set of calculations for how we get there.
The mission launched in 2018, but it isn't set to enter Mercury's orbit until November next year, 2026. Is that length of time purely for the reason, like you said, of getting the deceleration, and there's not an option for it to take less than, 8 years?
Yeah, realistically, at the moment with the technology we have, that's how long it takes. It took Messenger 7 years. It will take BepiColombo 8 years. That's kind of standard for us. And it was launched from the European Space Agency's spaceport, which is in Kourou, in French Guiana. And I went to see the thing launch, actually. Yeah, it was so amazing.
How was that?
So amazing. It was a night launch. So it's pitch black.
Wow.
And I was a few kilometers away. You don't get to be too close to it. And it just turned night into day as it launched. It was absolutely amazing to see. And although we're pretty confident it launched on an Ariane 5, which is a fairly trusted technology, there have been instances where things have gone wrong. So it's also a fairly nerve-wracking moment.
Yeah, of course.
As you watch this thing go up.
Well, it's a lot of work and it's a lot of money.
Yeah, exactly. Yeah. And hopefully my future research career is going to get to where it's...
a small amount riding on it, yeah.
So we were nervous, but it went really well. And actually what was really interesting was that it launched and no one said anything. We're there with all the project scientists, all the people that have worked on it. And then, there were a few stages that it had to complete before we were confident. And so you expect everyone to cheer when it launches, but no one does.
You have to hold it back.
Yeah. And then you hear the kind of telemetry coming back and these things have gone well and everyone cheers. And, it's just really interesting to be there in the jungle watching this process.
Gosh, I bet that's amazing to see going from putting together literally the instruments at such a small scale to then seeing it hurling into the air must have been quite full circle.
And knowing that you're never going to see it again. And you'll get the data back 8 years from now. So, yeah.
We were going around the Space Centre and someone said that one of the satellites, it was a lot smaller than they thought. Someone else said, that's because what launches doesn't all come back because obviously a lot of it detaches and separates. Does anything from BepiColombo come back or does it all just...
No, nothing at all. No, I mean...
Apart from data, obviously.
Your data comes back, but as you are orbiting around Mercury, the amount of energy it would take to get you travelling out of that gravitational well and back towards the Earth is phenomenal. Okay. So actually, our spacecraft will hit the surface. And that is how the missions traditionally end. You want this to be a very controlled end to the mission. And so the idea is that it will hit the surface, make a very small crater, and that will be the end of it. You don't want any risks involved. You don't want it to hit anything or, create space debris around another planet or anything like contaminate the surface. You just want sort of a very controlled finish to the mission. And I remember the Messenger mission, which I'd worked on for many years, ending, and everyone who was part of the science team got together, and we watched the final images of the spacecraft as the mission ended. It was quite a sad moment, really. We'd worked on it for so long to see the end of the mission. Yeah, it was interesting.
If you look at Mercury investigation, if you kind of zoom out and you look at the progression from Mariner 10 to Messenger, Messenger to BepiColombo, they each progress to the next kind of logical. First of all, it's a flyby, and then you're getting into the orbit of the planet, and then you're sending 2 proper satellites. What would the next logical progression be for the 4th mission?
We have already been writing some white papers looking at a lander on Mercury's surface. The challenge with doing that is that you're not, even if you have a rover, you're not going to go far. If you have a lander, you're going to land in one spot. So you have to land in the right spot to get the data back that you need to answer your science questions. And so you can't do that too early on. You need to really understand the environment well enough to make sure you're landing in the place that you need to land in, which sounds really obvious, but that's why, apart from the complexity of actually performing that maneuver, we haven't done that yet. But I suspect the next step in the decades to come will be that we may have a lander on the surface itself, possibly with some other spacecraft in orbit. We've done that at Mars. That's been, again, very similar progression at Mars, where you might have some orbiters and then you might have a lander or a rover, some other spacecraft in orbit. So that's what I anticipate happening. But that is a concept right now. So it will be decades before eventually that happens.
One of the leading edge instruments that was developed here down the road, within the kilometre of where we're sat right now probably, which is on BepiColombo, is the Mercury Imaging X-Ray Spectrometer, or MIX for short. You're a co-investigator on the MIX team, and this is a particularly exciting passenger on BepiColombo, as it's the first of its kind to ever go to any planet. First of all, what is an imaging X-ray spectrometer, and what type of things do we normally hope to learn from them?
MIX is designed to tell us about the surface composition of the planet. And so the way that works is that the sun is emitting X-rays all the time. And those X-rays are absorbed by the surface layer of atoms from Mercury. So they hit Mercury's surface, basically, and they get absorbed. And then an X-ray is re-emitted. And MIX travels along looking at the planetary surface all the time, and it will observe those X-rays emitted from the surface. So it's not the same X-ray that came from the sun. The X-ray gets absorbed and then re-emitted, and we see that X-ray. And the interesting thing that we can detect from this is that we measure the energy of the X-ray, And the energy gives us the composition of the material that absorbed it. So it can tell us it's a silicon or magnesium, or what is the element that absorbed that X-ray. And as we travel looking at the surface, we collect all of these X-rays and we're able to work out the large-scale composition of Mercury's surface. Now, the imaging part is what makes MIX so different. And that is done through some technology developed based on a lobster eye, actually, the way a lobster eye works.
Oh, wow.
And in essence, we are able to collect these X-rays, and our very complex optics and detector enable us to plot fairly accurately the location they came from on the surface. Previous instruments have just looked at a large area and said somewhere in this area there is some sodium or some magnesium or whatever. This instrument is going to give us incredible precision. So we'll be able to say, okay, well, there is the sodium or there is the magnesium. And so that will give us a much more detailed picture of the composition of the planet. And if you really want to understand how a planet has formed and evolved, you must know what it's made of. So the primary goal of MIX is to image the surface of Mercury in this unprecedented detail. And it also has an expanded energy range, which means we can detect more atomic elements than we've ever been able to detect before. And build up this picture of what Mercury is made of. And that's its primary goal. But interestingly, a few years ago, we were looking at data from the dark side of Mercury, the night side of Mercury. And we observed some X-rays coming off that dark side. They can't have been caused by solar X-rays because it's the dark side.
Sure.
So it wasn't they weren't being hit. That portion of the surface was not being hit by solar X-rays. It must be a different process that's causing these X-rays to be emitted. And we plotted out the location of these X-rays on the dark side and scratched our heads a bit and figured out that actually these X-rays are similar, analogous to the aurora that we see on the Earth.
Oh, wow.
So a completely different physical phenomena has caused these X-rays to be emitted. And that sort of process is that the magnetic field of Mercury interacts with the solar wind. Energy and momentum are transmitted into Mercury's magnetosphere and stored, and that energy builds up and up and up, and eventually is explosively released. And as that process happens, particles get accelerated, tied to magnetic field lines, and they hit the surface in two bands, much like we see the aurora at the northern and southern hemispheres, near the poles in the north and the south. We see the same at Mercury. There are some really interesting and tantalizing differences that we can't explain at the moment around where we see the X-rays at Mercury versus the aurora at the Earth. So we have a lot of work to do there. But actually, another part to this is that the instrument was already built and almost delivered by the time we had characterized these X-rays from Mercury's surface. And now we realize we have a whole new area of research we can do with this instrument that it wasn't designed to do. Its primary goal is solar-induced X-ray emission, looking at the day side and understanding the composition. And we now intend to look at the night side of Mercury using this instrument to tell us about the aurora, which just opens up a whole load of new physics that we weren't planning on doing. And it kind of highlights how when you start a mission in maybe the year 2000, I think this mission was begun, and you launch it in 2018, it gets there in 2026, that's such a long time. And in that time, the science that we know changes, our capabilities change, and we have to adapt. And this is a good example of that, I think.
So has the dark side been studied that much before, prioritized that much before, or is it a whole new eye-opening thing that it's got features that we'd be able to learn from?
Well, we had theorized that there should be a similar process of space weather that happens at the Earth. And as we observed with Messenger, we realized that space weather at Mercury is so much more intense and dynamic than we ever see at the Earth. And that's useful, actually, because if we want to understand space weather at the Earth, and particularly the harmful effects of space weather, so we think about it as generating beautiful aurora, but it can damage our power grids, GPS systems, give astronauts a high dose of radiation, disrupt the airline industry. It can have quite big and harmful effects. And of course cause damage to satellites, cause satellites to fall out of the sky. I mean, it can have quite profound impacts on humanity and society. And that's at the most extreme end. We don't see those events very often. We see those maybe once a century. The last one that we know of, the most extreme event we know of, happened in the 1850s. It was called the Carrington event. And we've seen smaller events since then, but these massive events are the ones that we worry about, because those are the ones that are going to impact society, but we never see them. And so the interesting thing about studying Mercury is that Mercury sees events like that every day, because it's a small magnetic field, it's close to the sun, and the dynamics are extreme. And so we see these huge space weather events. And that's why studying Mercury is useful, because we can try and understand the physics behind what's happening at Mercury and use that knowledge to help us understand what a big space weather event would look like at the Earth. And that analogy is really useful for trying to protect us from space weather.
You mentioned that the mix will be looking at the surface composition of Mercury. And when you see images of Mercury, it's almost quite moon-like in that it has a lot of craters and a lot of surface features. Will Mix also be looking at the features of those craters and things on the surface as well, or is it more looking at the surface composition as a whole?
That is exactly what Mix will be doing, and its advantage. So being able to image the surface and have these sort of pixels, if you like, where you can say in this spot there is this material, with such good spatial resolution, means that for the first time you can do things like look at impact craters. So as you mentioned, Mercury is covered in craters. Those craters were formed a couple of billion years ago in the late heavy bombardment. And because Mercury doesn't have an atmosphere, it has a tenuous exosphere, which means it has some bound material, but it's not like a thick atmosphere. A crater that forms weathers slightly over time, but largely looks exactly as it did when it formed. Now, as you have the impact of an asteroid with a surface, what you find is that the impactor is obliterated, but as you form that big hole in the surface, there's lots of ejecta or material that flies out as part of the collision, and that material lies on the surface, and it looks like rays coming out of the surface. And that material has been excavated. And so one of the things that we hope to be able to do is look at these rays and measure their composition. And that might tell us something about the subsurface composition of Mercury, which is a really difficult thing to measure with an orbiter. What is the subsurface composition? How do you do that? Well, these rays are going to give us an opportunity to do that. So impact craters are definitely a target for us, as are other geological features on the surface. The other thing that the previous mission Messenger highlighted is that there are some areas on the surface that they called low reflectance material, which tells you something about their physical properties, that we actually don't know what this stuff is. We have some theories about what this material might be, but we are hoping that we may be able to measure this material, which has been a big sort of source of interest on Mercury's surface, and actually determine what it's made of for the first time. The other thing that we see at Mercury is, a similar thing that we see at the Moon, is that at the bottom of the craters near the poles, some of these craters are very deep. We call them permanently shadowed craters. So they are deep and they're near the poles, and Mercury's rotation axis is at 90 degrees to the ecliptic, so it's sort of sitting up and rotating, unlike the Earth's, where our rotation axis is offset from the ecliptic, but Mercury's is in line. And so at the bottom of these craters, the sun never hits the surface. So they're permanently shadowed because the bottom of the crater is always in shadow. And although Mercury experiences incredible temperatures, it's close to the sun, actually we have discovered that there are deposits of ice in the bottom of these craters, water ice in the bottom of these craters. And that was actually first proposed using radio telescopes decades ago, which saw sort of radar reflective materials in the bottom of these craters. Again, we see this at the Moon. That's why everyone's racing to go back to the Shackleton crater at the south pole of the Moon, because it contains ice. But there's some interesting features around these ice deposits. How has the ice lasted this long? What is protecting the ice from sublimating? We don't know yet whether we're going to be able to analyze this, but this would be another obvious feature that we'd really like to explore. So we'll have to see whether we're able to actually answer some of these questions, but there are lots of questions about the surface that are a real mystery to us at the moment.
Does it ever feel like you're a marketing professional just speaking into the void? But with LinkedIn ads, you can know you're reaching the right decision makers, a network of 130 million of them, in fact. You can even target buyers by job title, industry, company, seniority, skills, and did I say job title? See how you can avoid the void and reach the right buyers with LinkedIn ads. Spend $250 on your first campaign and get a free $250 credit for the next one. Get started at linkedin.com/campaign. Terms and conditions apply.
Oh, Hilton stay, your beds are soft and cozy. No lumpy couch, no stiff futon, no shower line at crack of dawn. Oh, Hilton stay.
When you want holiday comfort you can count on, it matters where you stay. Enjoy comfortable rooms and friendly service when you stay with Hilton instead. Save up to 25% this season when you book with Hilton. Hilton for the stay. Terms apply.
Mix is obviously specifically designed for things that we want to measure in the context of Mercury, but because it's the first of its kind, if you like, to be sent to a planet, is the hope that if we get the learnings and the data back from it that we're anticipating, that it's the type of thing that we could then be sending on missions to other planets as well?
Really, this technology has a lot of uses. So no, it's definitely not specific to Mercury. It has visited one of the most extreme places in our solar system by going to Mercury, the extreme temperatures, the temperature gradients between the day side and the night side, the radiation that we experience in the inner heliosphere. So it's done pretty well and it's managed to survive this pretty hostile environment. But there are lots of other places that we could deploy exactly this technology to look at all sorts of features. So yes, this certainly won't be the end of the use of this technology moving forwards.
Once BepiColombo gets to Mercury, or gets into the orbit of Mercury next November, what then happens in terms of the anticipated timeline for getting data back? And what's the process of then what that data might look like and how quickly you can start using it?
This really depends on the instruments. So some of the instruments send back data that requires some processing in order to be usable, but you could use it fairly easily. Other instruments like ours require quite a lot of processing to get from the raw data to a data set that's usable. And that just takes time. You have to go through a data pipeline where you're taking this raw data and producing a data product. We will get the data back very quickly. I mean, it's taken us 8 years to get there, but the information gets back to us in a few minutes. So we don't have long delays in receiving data back from Mercury. It's of the order of 5 to 10 minutes, maybe, for a signal to leave Mercury and to reach us. So that part's really fast. The data will come back and we will already have in place the pipeline that we need to produce usable data. And eventually that data will be produced to the community so that anybody can download it. So you don't have to be part of the team. You don't have to be a scientist. You can download data and look at it. And that process does take time, of course. That process for it to be finally released, where we're all happy with it, takes months. But eventually, one of the principles of the work that we do is that our data should be available to everybody. So it doesn't sit behind a paywall. You don't have to buy it. These missions are funded through public funding, and therefore the data is available to all. So that's the basic premise of all the work that we do.
We're recording this episode up at the Space Park in Leicester, which is a huge hub of space research. So where does your research sit within this ecosystem, and what else is going on here?
There's so much going on here. In fact, we're sitting in a facility where we design and build spacecraft instrumentation to be launched out to the other planets. Which is just an incredible place to be. We've got cool people who are literally building things that are going to head out into the solar system. It's amazing. We've got some cutting edge technology here that enables us to do everything from start, designing the instrument to build it and deliver it, and then get the data back and then, do the science. So all the way from the concept to the research is housed here, which is really fantastic. And actually, I think that's a real strength. In fact, Leicester has had an instrument in space continually every year for the last 60 years.
Wow.
Yeah.
That's a crazy stat.
Yeah, it really is. So we really are kind of the heart of space physics in the UK here in Leicester. And even just my research group, we span all of the planets in the solar system, as well as, things like building the instruments, looking at the surface, looking at the environments, understanding the sun, all the way out to Uranus and Neptune, and comets and asteroids and all this kind of research too. And then we have a huge astronomy department and astrophysics department, and they do everything from computational modeling of two black holes colliding, all the way through to observing exoplanets orbiting other stars, which of course borders on the work that I do as well. So we have a huge breadth and range of research here. And yeah, I don't think people realize that actually if you want to think about space physics and astrophysics, this is a great place to come.
We'll be exploring Mercury, Saturn, Jupiter, all the planets probably in the Christmas lectures this year, as they're all about space. And very fitting that we're in Leicester. Obviously, it is intentional that we're in Leicester because the Christmas lecturer, Maggie Aderin-Pocock, is based up here in Leicester as well. But the Christmas lectures generally are all about getting kids interested in this science and making it more accessible to them and making it fun as well. And that usually involves blowing something up to get kids interested.
Great.
But if
Love
that's
it.
what works, if it ain't broke. You're also heavily involved in communicating your science. You won the Royal Society Rosalind Franklin Award back in 2021. So how did that interest come about for you? Has that always been something you've been passionate about doing throughout your research career?
That's a really good question, actually. So the answer is no. I used to just do my research and sit in a corner and, teach my students. And I always loved my subject, but I didn't really think anybody else would really want to hear much about it. And actually, this was a complete accident. So I applied to be on a BBC reality television series.
Yes.
Called Astronauts Do You Have What It Takes, which was this sort of slightly mad series where they were picking a group of people to go through astronaut selection. And they had thousands of applicants and they picked 12 and, they went down to one at the end. And I don't have a TV and had really no interest in being on TV. Okay. So I was the most unlikely person to be on the series. Yeah. But I was really interested and excited in having the opportunity to try all of these crazy things. And we did some really interesting things. I flew in a centrifuge and a microgravity flight and went scuba diving down to an astronaut training facility at the bottom of the ocean in Florida. And I took my own blood and like all these really cool things that you would never normally get the chance to do. And so that was a sell for me, was like, you have one chance in a lifetime to fly in a centrifuge, so you're going to take it.
Oh yeah, you got to do it.
Got to try. So I did this series and loved it. It was sort of took 7 weeks to film. We had 44 challenges. It was brutal and interesting. And I learned a lot about astronauts, but also about myself. And at the end of that series, I joined Twitter, actually, X, and just tweeted out, I'd love to share some of these experiences with people, get in touch. And my inbox was just flooded with thousands of schools. Like, I feel like every school in the country was like, come and talk to us, come and talk to us. I had all these amazing videos of me floating around in a microgravity flight or flying in a centrifuge or doing all these really fun things. And I received all of these requests and I decided I would just say yes to them all, because that's my personality. And I spent the next couple of years just driving around the country to any school that was interested and just talking about the stuff. And it could be a bunch of tiny primary school kids, or it could be a load of A-level students, or it might be some adult education centre, or it could be some brownies or some whatever. And it was exhausting, honestly. I spoke to about 50,000 children over a couple of years. It was huge and sort of took over my life. The way these things do. And I realized that actually, I had this opportunity to share this experience and to encourage more people to think about science, because maybe the things I'm talking about and the opportunities I've had are not necessarily what pops into your head when you think about a scientist. So I have the chance to kind of show people that you might have these amazing opportunities. And that's not just the astronaut series. It's, going on field trips to Svalbard to use radar systems to understand space weather at the Earth, or, all these amazing adventures that I've had as a scientist that I could share with people. And I thought that would be really popular, and then people would kind of lose interest. And after like a month or two, the whole thing would die out, and I'd done my bit, and that would be the end. But actually, it kind of went the other way. And like the more people I went to go and talk to, the more requests I got. And so that was kind of the beginning of me thinking, actually, maybe I have a bigger responsibility here. Maybe I can contribute in a larger way to the scientific community, not just doing my own research and teaching my own university students, but maybe I can play a role here. And so I did that for a few years, and it was pretty exhausting. I went from, Exeter to Northumberland to, over to Norfolk to Wales to Scotland to everywhere, just bouncing around, trying to do all of this alongside my job.
Especially when that's not something you were used to doing as well.
Not my job either. So I still had my normal job to do. So it was a pretty big undertaking, and I'm really glad I did it because it made me a much better communicator. It made me, if you can explain space weather to a toddler, then fair play, So it was really useful and it helped me in lots of ways. And I think it was beneficial. I still get emails and messages from people that I spoke to years ago saying, oh my goodness, I saw you in this place. And just to let you know, I'm graduating with my degree in astrophysics.
That's amazing.
It's really great. And then at the university, well, firstly, COVID came. And so obviously that kind of put a slight end to the flying around the country, talking to people in person. So there are a number of online events that began that I still do that attract maybe 250,000 people signing up. And I'll interview the head of NASA or the head of ESA or the lady who is driving the rover on Mars, or all these really amazing people, Tim Peake, a British astronaut. And people will log in from all over the world. And actually, while it's not the same thing as having me in person talking to you and, describing some of the amazing things I've got to do, it's a way to sort of reach out more broadly.
Yeah.
And then after COVID, the university really wanted to focus on widening access to higher education. So we really began looking at what the barriers are for young people to enter higher education or to study sciences more broadly. So is it that many young people perhaps don't know anyone that's ever been to a university, that can be an intimidating place? How can we manage to make the university more accessible to people, make people feel like they belong there, make people feel like, doing physics would be an interesting, exciting thing to do that would lead them to this incredible career. And it doesn't have to be a career like mine. There are 100 other careers you can do with a physics degree that are incredible. And we began to just design an engagement program that would support young people in lots of different ways. So that might be buying equipment for primary schools and having these loan boxes that go out to local schools in the area that have all the equipment you need to do a series of experiments supporting the national curriculum. Just recognizing that local primary schools probably don't have the resources to buy all this stuff themselves. With videos of us doing the experiments so the teachers feel supported in doing this, because experimental physics is important. And it's one of the first things to disappear when you're stretched, your budget is stretched. Yeah. People don't feel confident doing practical science in the classroom. It could be we run a homework club after school for young people in the area to come to the university, and we would help them with their homework, maths and physics preferably. Yeah. And, we had pizza, so we provided some food for people and just made this into a sort of community event. We ran a series of summer weekends, and this was with the support of the Royal Society, the funding the Royal Society gave me with this Rosalind Franklin Award. Where we invited people from disadvantaged areas around the UK to come to the university. We paid for their travel. We blew up rockets, we did space weather stuff. We used the lab equipment looking at X-rays, and we did some really cool, interesting science with them for a weekend, just showing them that the university is accessible, you're welcome, it's an environment where you can feel comfortable and you shouldn't be intimidated to apply to university if that's what you want to do. And we do lots of mentorship again with the local students and the community more broadly. So we just sort of started putting on this series of activities, many of which continue. We run a work experience program for young people who come for a week, and we just show them all the different science that we do in physics. So they get a little taste of astrophysics and cosmology and space science and planetary exploration and all of these different things. And they get to come to the space park and, do a day with our instrumentation specialists here. And really that's sort of where my focus has been most recently. Is I did this sort of speak to everybody as much as you can for a couple of years, and it was tiring and amazing and interesting, but it's hard to do long term. Yeah. And so now just sort of picking out areas of focus where I think that I can bring the most benefits to people, where I think I can have the most impact, I think has begun to be a real focus. And hopefully the projects that I've started will continue into the future. And, I'll keep getting these messages from people saying, oh yeah, I came on your space school and look what, I'm, now I'm doing a PhD. It's really great to kind of get that feedback.
Well, thank you for all the amazing work that you do. And I'm very excited to see what happens with BepiColombo, the mix. Maybe we'll have to get you back on the podcast to update when it gets into orbit and we can see what data we're getting. But Suzie, thank you so much for joining me.
Thank you for having me.
That's it for this episode. Thanks so much for tuning in. And make sure to tune in to Dame Dr Maggie Aderin-Pocock's Christmas lectures on the 28th, 29th and 30th of December on BBC4 and BBC iPlayer.
This episode is brought to you by Marqeta. When it comes to your payments provider, you can't afford to compromise. Marqeta's modern payment solutions flex with your business without the trade-offs. Stable and agile, secure and innovative, scalable and configurable. If they say you can't have it all, don't believe them. Your business demands more. Choose a payments provider that delivers more. Choose Marqeta. Visit marqeta.com/Spotify to learn more.